classes, you're welcome to do that. There may be some overlap just because, you know, people will struggle with similar things. Still could be useful though. Okay. All right. Where do we want to start first? What number? Yes. 37. Sure. Okay, so this one takes a few steps. So I mentioned this before, but let me just kind of clarify it. If I was going to ask any of these questions that have multiple different types of calculations. So like a stoichiometry calculation obviously has multiple calculations in it. That would be one type of calculation though. So if you have to do a stoichiometry problem and a gas law problem and a partial pressure problem as part of that, like I'm not going to give you 3 different parts or 4 different parts the way some of these do. It's really good for you to practice all of those, but I would only give you 2 of those parts. Like I'm pretty confident, I've written the exam already, I'm pretty confident I know that like my style is like 2 are fair, but not 3. Okay? So I'll show you what I mean by that as we're working through this. Okay, so let me pull this up so we can write on it. All right, so it gives us a mass of neon, a volume of the container, and then says it also contains argon. Okay, so the first thing that we know is that we're going to have to somehow consider Dalton's law of partial pressures. So the total pressure is going to be equal to the pressure of neon plus the pressure of argon. Okay, the volume's consistent because they're in the same container. The temperature's consistent, but the amounts as well as the pressure that each exerts is going to be different. So, in case you guys didn't know, a centimeter cubed, that's the same thing as a milliliter. Just stick that in your head for future use. I usually will write it as a milliliter just for that reason, but it's good to know. All right, so you're gonna have to convert this into liters, 0.75 liters. And your temperature is already in Kelvin, so that's good. And this pressure that's listed here is your P total. So you actually have, because you have the mass of neon and you have T, P, and V, you have enough information that you could calculate the pressure of neon. Okay, so let's go ahead and do that. So PV equals nRT. So pressure times 0.75 liters equals, now I'm going to have to convert this into moles. So 0.524 divided by neon's 20 something. Get it for sure. 20.180. Okay, so this is 0.2597 moles. It's probably more sig figs than I need. So 0.02597 moles. Times R, 0.08206 times 325. So I can solve for that pressure. And we won't actually go through like all of the math today. Sometimes I'll just kind of lay it out for you, tell you all the steps, but we won't actually solve it out unless people have specific questions. And if they do, great. Okay, so that is the amount of pressure that neon contributes to the container. And we know that the total is 1.14. So now we can just subtract 1.14 minus 0.923, and figure out that the pressure of argon is 0.217 atmospheres. Now, like before, we still have the volume and the temperature, and we have the pressure now, so now we can solve for the moles of argon. Then we're going to have to convert it to grams. So I'm going to do the same equation, PV equals nRT, but now I'm solving for N because I now have the pressure of argon. If it helps you, write like pressure of, that was weird. Pressure of neon, moles of neon. Pressure of argon, moles of argon. Because those are the things that change. The volume and temperature have to be the same if they're in the same container. Okay, so I have my atmospheres, I have my volume, 0.750. I'm gonna solve for my N. Oh, it doesn't wanna let me write a 0 there. I'm gonna solve for my N. R is 0.08206. Temperature is 325. And then the molar mass, once we get that, that's moles. And we're gonna multiply it by the molar mass, which is 39.9. So I get 0.00661 for the moles of argon, or 0.24 for the mass. This does say write it in 2 significant figures. If it doesn't tell you the number of sig figs to write it in, it'll tell you that you got the sig figs wrong, but it won't count the question wrong. If it tells you to write the number of sig figs and you don't, then it will count the question wrong. So you need to write this as 0.24, which is fine because you're studying for sig fig questions too at this point. So I have no problem with that. So I don't think I wrote this down anywhere. The moles that I got for argon were 0.0061 and the mass was 0.24 grams. Just total anecdotal, because I'm not sure, I'm just sensing it, but I'm getting a lot of gas questions. So if you haven't put a whole lot of effort into studying yet, like maybe start with gases, because it seems like that is a little bit less comfortable for a lot of people. And you get to practice stoichiometry in there too, so like maybe you don't need to do 4 quite as much because you're doing a more complicated form in chapter 6. All right, next one.
This is just but for a gas-evolving reaction, what 2 things have to be added to it for it to be gas-evolving?
You have to have something aqueous. The other doesn't matter. So sometimes it's 2 aqueous reaction or 2 aqueous things mixing. Sometimes it's a solid that's put into an aqueous solution. I can't think of one where we bubble a gas into a liquid and then a different gas is produced, but in theory you could do that. I'll give it a minute before I give up on you coming up with questions and I come up with one. I'll shame you on the fact that my other class filled all 50 minutes with their questions, but whatever. The assignment is set now. It didn't automatically do it. I had to go in and change it, but it is set now that if you do the rework, so you basically do the assignment again, but it doesn't affect your grade, it'll show you the right answers now. So you can use it as a study, but know that you know how to do it if you get it wrong.
You do
39? Yeah. And if you're the only one that asks questions, that's okay too. We'll fill the whole time with that. I don't know why I copied that. Okay. So, the reason why this, I've seen 3 different ways now that people approach this, and the one I saw yesterday, I was like, oh yeah, that totally is the least amount of math that you would have to do for this. So I'll show you that one just because it's quicker. But the reason why this one is difficult is because it says calculate the total volume of gas, and this reaction has 3 gases being produced. That is why this is hard. So in theory, your final volume is going to be defined by the pressure of N2, the pressure of O2, and the pressure of H2O. Or another way of thinking of that is the moles of N2, the moles of O2, and the moles of H2O. I just did pressure. Because pressure and moles are proportional to each other. And if you're talking about a mixture of gases, everything else is constant. So if you have, like let's say you know that neon is 2/3 the amount of moles, it's also 2/3 the pressure. So you're kind of using that idea here. An easier way to do it though is to not worry about each individual gas and just consider them a gas altogether, because we know that as we add up their individual pressures, how they each contribute, that's just going to be equal to the total pressure. And if we add up all their individual moles, that's just going to be equal to the total moles. So we do not have to account for the type of gas. It doesn't matter if it's neon or nitrogen or oxygen, it just matters how many moles. So I'm going to kind of rewrite this equation and just say 7 moles of gas. Okay, so there's 2 nitrogen, 1 oxygen, and 4 water. I'm just using those coefficients. So there's 7 total moles of gas. So what I can do is take this starting value, 1.75 kilograms of ammonium nitrate, obviously I'm going to convert that to grams first. Then I'm going to do molar mass. I was pretty generous on the test. I didn't, not every single little question, but most of them I gave you the molar mass. Sometimes I didn't want to because I was like, if I put that in there, they're gonna know that they have to use the molar mass. And I don't want them to have to know. I want them to figure out that they have to use the molar mass. So I didn't. Okay, so this is ammonium nitrate. I'm just gonna write AN. So now from the balanced equation, so I converted this whole process, converted to moles of ammonium nitrate. That's what we do in stoichiometry every single time. How did I know I had to do that? Because ammonium nitrate is not a gas. It was a reactant. It was a solid reactant. So I can't calculate volume of a gas until I know how much gas there is. So I do the stoichiometry, moles of ammonium nitrate, and then I'm going to use the balanced equation to say 2 moles of ammonium nitrate form 7 moles of gas. And that will now tell me N total. So the point I want to get across is that to find P total, you need, I guess we're solving for V. So I'm going to write it like that. V equals nRT over P. So I can do this P total and N total, or I could do it for each individual gas. Okay? They give me the P total though, so that's going to be the most useful. All right, so let's do the stoichiometry problem. 1.75 times 1,000 divided by 80.049 times 7 divided by 2. So total moles is, that seems huge, but I guess we were dealing with kilograms, so that shouldn't be that surprising. 76.5 moles. And then we're going to go ahead and just plug that in up here because we're looking for volume. So 76.5, sorry, times R, 0.08206, times the temperature, we need to convert to Kelvin, 119 plus 273.15. Every time, don't get caught by thinking for some reason in this problem I don't have to convert to Kelvin. In gases, you always do. Okay, and then the pressure, 730 millimeters of mercury. So I need to convert that to to atmospheres. So I'm going to divide by 760, and I get the pressure to be 0.961 atmospheres. And that should give me the volume. And do they say the number of sig figs? They don't say it. This one is in 2 though, technically. I hope they noticed that when they do it because there's not a point at the end there. So I'm gonna report this in 2 as well, which it's 2,561. So reporting that as 2 sig figs is going to be 2,600. Okay, on an exam, how would I test this question? I like everything except I would put everything so you didn't have to convert the units. So I would give you the temperature in Kelvin, I'd give you the pressure in atmospheres, I'd give you this in grams, and then maybe I would be a little bit, give you a hint by saying the total calculate the total volume of gas at, the temperature and a total pressure of such and such. So that and maybe I would say, calculate the total volume of the gases produced, nitrogen, oxygen, water. The problem itself is fine. I just would probably word it a little bit nicer. Because to me, that's only 2 calculations, right? It's a stoichiometry calculation, and then it's a PV equals nRT calculation. Yeah. 22? Okay. Okay. Stop it. There's got to be a way. Oh, man. Okay, let me refresh this for a second. There's got to be a way to tell your iPad to just let you... anybody know what the screenshot, keyboard thing is? Or power and volume or something? Yeah, that worked. Okay. I'm also supposed to be able to drag from the bottom. Anyway, you should be able to write on it without having to take a screenshot or something or save a file, I think. Okay. End answer is asking, okay, it's one of these. Yeah. This is the hardest type of limiting reactant problem that we've done ever. And I think I told you guys I would only give one limiting reactant problem on the test. So if this was on there, there would be no other limiting reactant problems in the whole thing. Okay, I'm gonna write down, because for some people, it is better to have a formula of the steps you have to go through for this type of problem. If that doesn't work for you, or if you feel like you're not gonna remember those steps, think of the pizza and cheese example. So here, we've got 10 cups of cheese in the fridge and 3 pizza crusts, and I figure out that I can only make 3 pizzas, and I have to work backwards and see how much cheese I used and then subtract it from the 10 cups. That's the thing we're doing, okay? All right, so we have 2 reactants. Now let's pretend this was just a straight limiting reactant problem. We have 2 reactants, so I immediately know that I'm gonna have to do 2 separate stoichiometry problems and pick the smallest product made. And that's my actual amount of product made. Now in this equation, they don't tell you which product to look at, so it doesn't matter. You can do either one. So let's look at the iron chloride because it's the first one. No good reason, okay? So we are going to do 2 calculations, figure out the moles of iron chloride produced, not because we care about how many moles are produced, just because it's going to help us know which one is the limiting reactant and which one is in excess. Okay, so the first step is going to be determine the limiting reactant. I am really struggling. Maybe I need a new tip or something. Determine the limiting reactant. Okay, so let's go ahead and do that part first. 250 moles of iron sulfate. And I'm gonna do a mole to mole conversion. This actually just happens to be 1-to-1. So if this was the limiting reactant, I would make 0.25 moles of this product. I can't tell what's going on. I'm gonna start saving these as files. I think that would work better. Okay, with the other one, 0.648 moles of HCl. Now it's a 2-to-1 reaction. I like that they give it to you in moles because just one less step for you to have to do. So that would be 0.324 moles of the product. Cl2. It doesn't want to let me write there. Cl2. Okay, so this is how much product is produced, but I don't care about that. All I care about is that that told me that this is the limiting reactant. So a question like this could ask, how much FeCl2 is produced? It could ask, what is the limiting reactant? Now we know both of those answers. In this question, it's the hardest of the questions. How much of the excess reactant is left over? So what we're saying is that this one was in excess. This was the bag of cheese that we didn't use all of. And now we need to know how much of that cheese did we use? Well, the way we figure that out is by taking how many pizzas we made, the 0.250 pizzas, and saying, how much cheese did we use to make those pizzas? So it's still a stoichiometry problem, but we're working backwards. So determine the limiting reactant. From the product, you're gonna work backwards to the excess reactant to figure out, oh, I made 3 pizzas, so I used 6 cups. So 1 mole FeCl2 for every 2 moles HCl. I swear I did this. Oh, it does change the numbers sometimes. But I swear I did this the other day with you two, and it was not the same number. Maybe they changed them on me. I hope I didn't do something wrong. I'll check it in a second. Okay, so this one is 0.5 moles of HCl was actually used up. But I had 0.648. So I used up the 0.5, so left over I have 0.148 moles left over. Now I have to see if I can figure out why that didn't feel like it did the last time. No, I can't figure out why it looks different to me. So the last step here, you work backward to the excess reactant, and then you take the original amount of the excess and subtract the amount used of the excess. And then that tells you how much is left over. Like I said, I could do one like that, exactly like that on the test. That would be the only limiting reactant question that I would give you, though. Which one? 40? Okay. Let's try a different way of saving this. See if my... Okay, yeah, I did this one in my other class, so I remember that it was, oh, come on. She's not behaving today. Okay, let's open this in Files. Get a little bit easier to work with. Okay. All right, so the first thing is this question was intended to be a homework question from Pearson. So they were like, oh, they can go look up what the pressure of water is at 25 degrees C. You would never, I would always give you that. So I'd either give it to you in a table where it's different temperatures and different pressures of water, or I would just tell you the partial pressure of water is 23.8 at 25 degrees C, okay? Because you have to have that in order to solve this problem. All right, you've got this reaction. You're starting with silver. You're producing silver, and you're also producing oxygen. And they want to know the volume of gas. Yeah, I'm sorry, I was rewording it how I would say. What total volume of oxygen gas is collected over water from that amount of silver with a pressure of this and a temperature of that? The key point in this reaction is to remember that the total pressure is equal to the pressure of the oxygen and the pressure of the water. Okay, so the pressure of the total pressure is this one, 762. And the pressure of the oxygen is the thing we want. And the pressure of the water is this thing that I would give you in the question, 23.8. So we're going to subtract to get the pressure of oxygen. The question asks for volume, though. So this one is 3 parts. I would give you 2 of these. So we're going to need to do nRT over P. We have temperature. Just need to convert that into Kelvin. We have R. We're finding out the pressure of oxygen, and then we will convert that into atmospheres. We don't have the moles yet, though. Okay, so we have gotten almost all of our components, but not the moles. So this one also involves a stoichiometry problem. So there's a partial pressure problem, a stoichiometry problem, and a PV equals nRT problem. I would limit that to 2 of those types of calculations. So maybe I would just give you the moles of O2 and skip the stoichiometry part. Good for practice, hard when you are in the middle of a test. Okay, I think the molar mass of silver is 107 something. I'm sure there's an app I could download that just has a nice periodic table that I can zoom in on and stuff. Okay, from the stoichiometry, 4 moles of silver for every 1 mole of oxygen. So the moles of oxygen, 16.7 divided by 107.868 divided by 4. So I'm going to go ahead and put that in this equation, 0.0387 moles of oxygen are 0.08206, T 298.15. And then I just need to finish this pressure calculation up here. So I'm subtracting to get the pressure of oxygen, 762 minus 23.8. So I get 738.2. And I'm going to divide by 760 to get the pressure of just the oxygen in atmospheres. Now I can go ahead and plug that in down here to get my volume. So you guys are doing good. 35, you've asked lots of questions. What next? Yep. 14? 13. Okay. Oh, I don't think that did that right. Let's press the other button. Ooh, I like this because nobody else has asked about this yet. And it's been a long time since we did these two. Okay. Percent composition. So percent composition is going to be the grams of the thing you're looking at. So in this one, it says oxygen is what we care about, over the total grams of the molecule, or HC2H3O2 in this case. And then because it's a percent, we'll multiply by 100. So in this case, we have to go ahead and consider all of the oxygen that's there. In this molecule, there's 2 atoms. And so we're going to just take the 16 times 2 and do 32 grams of oxygen. And then acetic acid, we need to add up the total molar mass there. So 12.01 times 2 plus the 32 from the oxygen plus 1.008 times how many hydrogens? 4. So the total molar mass is 60.052. And then we just take fraction of that and multiply by 100. So this one is 4 significant figures, 53.29% oxygen. Now, clarification, the only reason it was O2 had nothing to do with the fact that O2 is diatomic, that oxygen is diatomic, because it's in a compound. The whole diatomic thing only comes into play if you're talking about oxygen by itself, and not even in a calculation by itself. It just happened that there were 2 atoms in that molecule. So like if it had asked us to do this for hydrogen, we would do almost the exact same calculation, but we would now put hydrogen times 4 on the top. So 1.008 times 4 for the grams of hydrogen over 60.052 total for the acetic acid times 100. So that would tell us the mass percent of hydrogen in acetic acid. Any others? Yep. 38, yep. This is that one we did the other day, I think, right? Someone else asked about a question like this, and I was like, oh, is that one that I hated? I hated explaining it. That was what it was. But I think I've gotten to a good explanation. Okay, my screenshot.